Hello again, and welcome to episode 2 of our 2019 WPI Library programming tutorial. My name is Joe Wilson, head coach and mentor of Manning Robotics, Team 4627. And today we're going to start actually getting into the nitty-gritty, starting to look at the code, starting to add in our drivetrain and get something drivable by the end of this video. And if we have time, we'll start doing some automation stuff as well and getting some little building blocks made of having the robot drive forward and backwards a little bit. And have a bit of fun with that. For a quick recap of what we covered last time, we talked about the general architecture of the command-based framework, at the center of which is this robot class. And the robot class is kind of like your main in that it's what is creating everything else that's to happen on your robot. One of those things is your subsystems. So this is like your drivetrain, your shooter, your lift. Again, this was any independently acting mechanism on your robot. The robot also creates something called an OI. This is just a class for handling all of the controller inputs. And then kind of as a sidebar, we've got this idea of commands. And commands are kind of like the menu of building blocks of actions that your robot can actually do. And then ways of combining those in interesting ways to do complete sequences of tasks. Lastly, there's just this file called robot map, which is just a nice convenient place to store all of those magic numbers, those constant terms, and we'll be using that in this tutorial for sure. So before we get into it, I'm just going to take this template that we created last time. We're going to do a little bit of cleaning up, just get rid of some of this example stuff so that we're ready to go. So for example, we're going to get rid of this subsystem. This example subsystem. I'm just going to go right ahead and delete that. Yep, get it out of here. And that's going to cause some errors to come up, absolutely. We will solve those in a sec. I'm also going to get rid of this example command. I don't want it. Get it out of here. And we will see in robot now we're going to get some issues. We'll get rid of these imports. We don't need those. So here's where the robot is creating an instance of that example subsystem, which we don't need, so get it out of here. I'm also going to get rid of some of this sendable chooser stuff. Yeah, let's just get rid of that. This is all, okay. The sendable chooser stuff that's already in here is a way of setting it up so that you can choose your autonomous mode on your smart dashboard before the match begins. We're not going to use that for this, so I'm just going to get rid of it just to clean things up. We'll go through here. Okay, there's some of this. We don't need this. We don't need this. And we don't need this. And there's still some errors somewhere. Where are you? Let's find out. Ah, silly me. Okay, we're good. We're going to save all that. Beautiful. Oh, some more imports. Okay, now we have a cleaned up template ready to go, and we're ready to start mucking about with creating a drivetrain. So we've got a bit of a sequence that we're going to follow here. Our end goal is to have a drivetrain on our chassis that we can drive around with a controller, but that we can also say, okay, move forward for a little bit, turn for a little bit, move forward for a little bit more. Just something basic, just to get a hang of things. In order to do that, first we need to make a subsystem that's going to represent our drivetrain. And then we're going to make some commands that will handle both the operator input stuff and also a command that will handle just like the automated moving forward. In order to do the operator input stuff, we're going to need to tinker around with the OI class in here and add some getters for the various axes of our controller. And we're going to have to make sure that we add some stuff back into robot to make sure this stuff actually happens. So let's begin. We would like to make a new subsystem. There's a few ways of doing this. Probably the easiest way is just right-clicking on your subsystems folder and saying create new class/command. And I'm going to say I would like a subsystem. And we'll give it a name. I'll call mine drivetrain. Chassis, whatever, I don't know, whatever you want to call it. We'll use drivetrain. So we'll see over here in our browser that the template has created inside subsystems this drivetrain.java, and it's automatically added a little bit of stuff into here, same stuff that we saw in the example subsystem in the previous video. So this class drivetrain extends subsystem. So it counts as a subsystem for all intents and purposes and has some other functionality going on, not defined in this class, but defined in the definition of a subsystem. Cool. So what we do in a subsystem first is create the objects that refer to all of our hardware components. So in the case of a drivetrain, we've probably got some motor controllers. I'm going to just kind of assume that you're working off a kit of parts robot, so you've got 2 motors on the left and 2 motors on the right. And in this example, we're going to be controlling those using Talon SRXs. That's just because that's what we use. But a lot of this stuff will translate to whatever motor controller you happen to use. Now, before we make a Talon SRX object, we actually have to make sure that we import into this project the CTRE third-party library. So in order to do that, we need to manage third-party libraries. Now, exactly where to find that setting in here, you don't need to know. All you need to know is basically what you're looking for. Remember from last time that we can access the command palette with Control-Shift-P, and that's Command-Shift-P on a Mac. And then we can start typing vaguely what we want to do. So we know this is something within WPILib, and we want to do something about, vendor libraries. I just typed M, but I was going to type manage. And you'll see manage vendor libraries comes up here. So I'll hit enter. We get some choices, and I'm going to install new libraries offline because I've already downloaded from the CTRE website their installer for their own libraries, the offline version. This is all, of course, in the docs on the Screen Steps Live that we went over in the last video. You can see I have some options here, CTRE and Rev. We're just using CTRE right now, so I'm just going to check that and hit OK. Let it think for a little bit. Some stuff's going on in the background here. The main one that you might notice is this vendor deps folder has appeared with this phoenix.json. This is basically the reference to where to find the libraries. Guess what? You don't need to worry about that. You've done the work of importing the libraries. It's now in there. We can now use it. So let's make some Talon SRX objects to refer to our motor controllers. So Talon SRX, we'll go motor left. Well, I should be proper here. Motor left 1 equals new Talon SRX device number. So this is the CAN ID of the Talon SRX. So maybe you've got him set to be 0, 1, 2, 3. Okay, so we could put 0 in here. But, this is a magic number. This is one of those constants that's not really going to change as the code runs, but we might need to change it down the road as like hardware changes. So this is something that should actually go in robot map. Now, instead of actually going into robot map and putting it there, I'm just going to pretend it's already there, and we'll see what happens. Robot map dot, and let's call this motor left 1 ID. You and your team have to decide on your own system of naming things. We use the all caps with the underscores for our constants. But you see we get a little error here. Robot map cannot be resolved to a variable. Now, if you click on an error and use Control period, that's going to bring up the quick fix menu. And the first one here is to import robot map. Hey, that would probably be a good quick fix. So now we've got robot map imported, but robot map does not contain anything called motor left 1 ID. So again, we'll go Control period, and we'll see some options. And one of those will be to create a constant motor left 1 ID in robot map. Let's do it. You see VSCode opened up robot map for me. And if we go there, we can see it already added this public static final int motor left ID equals 0. It's going to default to 0 whenever you do that. We could have gone in here and just typed this in ourselves, but it's kind of nice to just continue in your flow and then go resolve those errors later. So it's public, of course, because we need to access it from other parts of the code. It's static and final. We don't want this to ever be edited by anything in the code. It's just this constant. Okay, and in this case, it's an int. You might have to change the type if what you're referring to here is a double or whatever else. So there we go. We've made a Talon SRX. We've made one of them. Let's go ahead and copy and paste this a few more times. And we're just going to change the name here. Motor left 2, motor right 1, and motor right 2. And left 2, right 1, and right 2. Great, and we've just got these errors to go resolve. Do that, please. Do that, please. Do that, please. And now at your leisure, you can go back into Robot Map and actually change these. Let's just get rid of these comments. So maybe I've got my Talons configured to be numbers 0, 1, 2, 3. Whatever yours are configured to, set your constants here. Okay, this is great because if you ever change those, if maybe you find that a Talon isn't working and you've got to replace it with another one and you don't have time to go reconfigure its CAN ID, but you know its CAN ID, you just have to go back into Robot Map and change this number. You don't have to go digging around for where that declaration is. Awesome. So, okay, we've got those motors. The next thing we want to do in a subsystem is create the methods for controlling our actuators or getting information from our sensors. In this case, we want to be controlling some actuators. We're going to be defining the only way to control these objects by other parts of your code. And because of that, we actually want to make all of these private. Okay, we don't want any other parts of our code directly accessing any of these actuators. And it's just saying they're not used. That's fine. We will use them in a sec. We want to dictate exactly how and when other parts of the code can access these. For example, you've got 2 motors plugged into the same gearbox. Okay? If you're not careful, somewhere else in your code could accidentally ask those 2 motors to spin in opposite directions and either do some damage to the motors, just draw a lot of current, or maybe do some damage to your gearbox. And at the very least, it just won't work. So we want to be able to control that and make sure that whenever someone's trying to set the left motors, they're setting both of them. And this also lets you do things like, maybe every time you set the left motors, you want to print out to the console what that value was for some debugging purposes. Okay? In what we're going to see here, you could control that kind of thing. So we're going to make a couple of methods. They're going to be public. They're going to be void. We don't care about them returning anything right now. And we'll just say set left motors. I'm going to be upfront with you here. There's lots of optimization that could be done in what we're going to cover. I'm trying to do things in a way that are easy to understand, a little bit simplified, maybe simplistic, but probably and definitely not the most optimized way. So feel free to comment on this video if you know of a better way to do something that I've done. But if you're way ahead of me, that's even cooler. So set left motors. This needs to take in a double, and we'll call it speed. So somewhere else in the code, we want to set the left motors to a certain speed. We're going to use this method to do that. So what should this method do? This one should say motor left 1 dot set, and we have to, CTRE did some weird things to their library in the last couple of years, so we have to do a couple things here first. First we have to say control mode dot k dot percent output, and then the speed. And we need to do the exact same thing for left motor 2. Great. So now any other part of the code that wants to control the left drivetrain on our chassis has to use this method to do it, and this will absolutely make sure that whenever they do it, that both of them get set to the same percent output. So that's nice and safe. We want to be able to do the same thing for the right motors. And we just need to change this and this. So we now have a method for controlling the left motors, a method for controlling the right motors. And these would work right now. But let's think about this for a second, about the orientation of those motors. They're pointed in opposite directions. So if these motors turn clockwise and these motors turn clockwise, your robot's actually going to turn, okay, because they're facing in opposite directions. So we actually need to reverse one of these. Now, there's a few ways to do this. One is you could, in the constructor of drivetrain, you could call something like motor left one dot set inverted, and you can tell that it's inverted. You can do that. You'd want to do that in the constructor, not in here. But here, just because we're doing things quick and dirty and getting you off the ground, we're just going to do this. So if you pass in a positive number to the left motors, it's actually going to set their percent output to the negative of that number. And if you send a positive to the right motor, it's just going to send that same number. So this will make one of your drivetrains the reverse. And so if you send them both a positive number, you should go forward. Now, you might go backwards. You'll have to double check and see what happens later on. And if you're going backwards when you think you should be going forwards, just take the negative off of here and add it into here, and you're good to go. For now, this is all we need to do in drivetrain. So the takeaway message here is that your subsystems should be really clean and crisp. There's not a lot going on. We're creating the objects, and we're making some methods for controlling those objects. And that's it. We're not talking about any logic of when or why or how. Just do the thing. What can we control, and how are we going to control it? So let's just save all, Control KS. If you're ever unsure about a hotkey, if you go to the command palette, that's Control Shift P, and search for the command you want. So my example was save all. You'll see that it shows you the hotkey, Control K followed by an S. Nice. So we're done with drivetrain. For now, we're going to come back in a little bit to set the default command once we have one. Our next step is to do something with the driver controls. We'd like to be able to do some stuff on the controller and have the robot respond. In order to do that, we're first going to need to take a look at OI and create references to the joysticks themselves and make some methods for getting back the values from the axes. So there's some comments in here that tell you a little bit of how to do this, but we'll just go through like this. So we're making a joystick object. Now there's a few options here actually. You can use joystick. You can also use, if you're using Xbox controllers, I believe, yes, there's an Xbox controller. So we're using Xbox controllers, so we'll use this class. I think it's almost the same as the joystick class. I think it actually extends joystick, so it's going to work much the same way, but why not? We'll call this driver controller equals new Xbox controller and the port. Okay, you're going to plug in, you can have multiple USB devices plugged into your driver station. If we open up driver station, I'll show you where to find that if you don't already know. Down here under the USB signal symbol, you'll see any USB devices you have plugged in. And you can drag them around to make sure that the right controller is in the right slot. But your default thing that's plugged in, right now it's actually my mouse, but if you have a controller plugged in, that'll be 0. So maybe you want to make your driver controller be port 0. But, we shouldn't do this. We should put this in robot map. So again, robot map dot driver controller. And it's saying that doesn't exist. Okay, make it. Again, that was control period to bring up that quick fix menu. We hop over here and now it's in there. Great. So we've got a controller object. We need a semicolon on there, of course. Now we need to make ways of accessing the values of that controller, the axes of the different, the sticks and the triggers. So we are going to make a method that is going to be public. It's going to return a double because we're returning the value of an axis. And we should make this private just to be safe. And we will call this get driver raw axis. and we need to pass in an int, and that will be the axis number. So basically, somewhere else in the code is going to say, hey, I would like to know the current value of the left stick y-axis, or the right trigger. And so we're going to return that, and that value comes back as a double. The way we get that is driver controller dot get raw axis, and then the axis number. Oops. Something's wrong. Oh, and we want to return this. Hey, okay, so that's happy. Good. That's actually all the work we have to do in here for now. We just have a reference to a joystick object that's going to be plugged in to one of our USB slots. And we have a way of accessing the value of a specific axis at any time we want. So we will Control KS save. And now we're going to go ahead and make a command for actually driving this thing around. So we're going to click on the commands folder, create new class or command, and we'll create a command. We will call this, let's make a tank drive for now. And then we'll talk about some more advanced ways of driving a robot. So we'll see in the commands folder, it's created tankdrive.java. We've got this class that's been templated out. It extends command, so it counts as a command, and yada, yada, yada. All of these things that we went over in the first video. So let's just start from the top and work our way through. So first things first, the requires here. This is where we get to tell the scheduler, does this command use a subsystem? So that if any other command comes along and says, hey, I'm using that subsystem now, the scheduler knows to cancel this one to make room for the new one. So in this case, we want this command to require the drivetrain. But we currently don't have an instance of this drivetrain class. Remember, so far all we've done is define it. It's a Java file existing in our folders, but there's nowhere actually making an instance of drivetrain. That happens in robot. So we'll go back into robot here. Right inside it, we will make a public static drivetrain. Is that my drivetrain? Yes. We will call it drivetrain, just for simplicity's sake, equals new drivetrain. And there's no arguments. Cool, save. And back in our tank drive command, we can now say this requires robot.drivetrain. So we have to tell it for requires, we have to tell it the specific object, the actual instance of the subsystem that it requires. Not just the class in general, capital D drivetrain, but the instance of drivetrain, lowercase d drivetrain. Okay? All right, let's work our way through. Initialize is where we put any code that needs to happen as soon as this command starts running, and this only happens once. So in our case right now, we want to be continually controlling the motors from our triggers, for example, or maybe our sticks. And so we're not going to put anything in initialize. So let's move on to execute. This is the method that's called every time through the robot loop. Every time through robot periodic. If we look over in here, robot periodic, or actually anytime through teleop periodic, scheduler.getInstance.run is called. And this tells the scheduler to go through all of the active commands, and for each one of them, run their execute method. So in here is where we're going to put our get the value from the controller and then send that value to the drivetrain. So let's do this in a couple steps and break it down. We're going to make a sort of a temporary variable here. Double, we will call this left stick y equals, and this is going to be robot dot, oh, what do we call it over here? They used this syntax, MOI. Okay, that's just some syntax, you know, whatever. You can use that if you want. MOI dot get driver raw axis, which is the method we just created. And now we have to give it an axis number for the left stick Y. Okay, I don't know it off the top of my head. Rather than search it up, what you can do is plug in your joystick, highlight it here in the USB folder or the USB tab on the driver station, and move that axis around, and you will see these bars moving, and that'll tell you the number that it is. So I don't know them off the top of my head, so what we're going to do is hop over to our repository of our current code, and we'll find it there. Oh no, not in OI, it's going to be in robot map. Here we go. Left stick Y is 1, and for the record, right stick Y is 5. Okay, cool. But we don't want to put that number here, 1, right? Okay, robot map. Get comfortable doing this. And we will call this left stick Y. Boom. This is not imported. This does not exist. Create it. And it is supposed to be 1. Okay, we're going to do the same thing. We'll get the right stick Y. Oops. Stick to your conventions. And that doesn't exist. Create it. Make it 5. Okay. Let me explain a little bit about what we're doing here. Tank drive, what I'm referring to, is where you have one axis controlling one side of your drivetrain and another axis on your controller controlling the other side of your drivetrain. So it's hard to drive, but for the purpose of this example, it's a nice simple way to get something moving. So in this way, if you go both sticks forward, the robot will drive forward. If you want to turn, you're going to have one forward and one back, or one not quite so far forward. And if you want to turn the other way, you reverse that. If you want to go backwards, both sticks backwards. So it's hard to like go in a straight line slowly with this because you have to get both sticks at the exact same position. But you know, just as an exercise, we're going to go through and do this. So right now we're getting the value of the left stick Y and the right stick Y. Now we want to actually take those values and send them to the motors. So we're going to say robot.drivetrain.set left motors. Okay, this is what we just defined already in Drivetrain ourselves. The speed we're going to send it is this left stick Y. And we'll do the same, robot.drivetrain.set right motors, right stick Y. Great. Done. We've done it. We have made a command that every time through the loop takes the left stick Y and sets it to the left motors, takes the right stick Y and sets it to the right motors. And you can, once in a little bit, you'll be able to upload that and fiddle around with it and see if that works to your liking. One thing you might find is that it might be very sensitive. This driver controller.getRaw axis returns a double between -1 and 1. Your motor controllers in here, when you're saying set, it's looking for a double between -1 and 1. If you give it 1, that's like all ahead full, go crazy. What you might want to do in this tank drive is actually scale this. So you might want to say, multiply this by like 0.5 and this by 0.5. Now actually you will want to put these scale factors in your robot map, but for now, just as an example, that would be a way to turn down the sensitivity. Another thing you could do is you could actually like square these, which would be kind of interesting. Oh, that's not the right operator. You could multiply it by itself though. And what that'll do is that'll actually get you an exponential scaling so that it's not so sensitive close to 0 and it gets more sensitive the further away you go. That might be helpful, I'm not sure. You could do all sorts of things, but we're just going to leave this as this for now, for illustration. If we keep scrolling through, we actually don't need to touch a lot here. IsFinished is the method that's called by the scheduler every time through the loop, immediately after it calls execute. So for every command that's running, it calls execute is finished. Execute is finished. Execute is finished. If isFinished returns true, that tells the scheduler that this command is finished, and we can get rid of it. We can end it. Otherwise, it's going to happen again the next time through the loop. So by saying isFinish just returns false means that this command never ends. And that's kind of what we want, because this is going to be the default command for your drivetrain. So whenever nothing else is happening, we should be able to control it. Now, one thing you might want to do in end is something like robot.drivetrain.set left motors 0. And same for the right. As a kind of just in case. Because motor controllers preserve the last input that was given to them. So unless you tell them otherwise, it's going to keep going at that % output until you run into something, or you run out of batteries, or you disable the robot. So this is just a nice way of making sure that if anything else is going to happen with this drivetrain, that we first stop whatever we're doing. And it might be worthwhile in here to do the same thing, or you can actually just call end. This dot might be a safer way, but I think you actually don't need the this dot in Java. Control KS to save all. Now we're very close to having this be able to actually run. The one thing that we're missing is we have this command, but this command is never actually added to the scheduler's list of commands that are running. So there's a few ways of doing that. You can tell it to run at the start of a mode, but we also already know that we want this to be the default command for the drivetrain, so we're actually going to use that in here. So we're going to say set default command new tank drive. And it just doesn't know what tank drive is. We are going to say go ahead and import that, and now everybody's happy. Okay, so one thing to note here is that we have told it to create a new instance of tank drive right here as the argument to this set default command. This is the kind of thing we'll see over and over again when we're using commands, assigning them to buttons or adding them to command groups, is that we always make a new instance of the command. And then when that command is finished, it gets destroyed and frees up that memory. You don't have to worry about all that stuff, but you do have to know that it's a new instance every time. So if you've got some logic with some local variables inside that command, those aren't going to be preserved the next time that command gets called. So you have to come up with some other ways of handling those things if you want some values to persist command to command to command. So right now we actually have code that we could upload to a robot and run, and you would be able to tank drive it around. In order to do that, you just need to know how to deploy to the robot. So if you have a robot in front of you, which I don't, it's being built on right now, you could either plug in via USB, Ethernet, or over the Wi-Fi if you've got your radio configured. Once you're connected, and you verify that you're connected because your driver station will tell you that communications light is green, you can then go into here and go Control-Shift-P to bring up the command palette, and then WPI, and we want to deploy. There it is, WPILib deploy robot code. I'm not going to click this right now because I'm not connected to a robot. What you can do just for verification purposes is call WPILib build robot code. And this will do the actual building of the code without actually sending it to a RoboRio. And so this is just a way to verify that nothing's going to break when you try to compile the code. And we'll see, look, it was successful. Hooray. And it did a lot of stuff that's beyond me. So that's cool. If you were to go, well, here, let's just see. If we go deploy, we're going to see it build it first down in this little terminal, but failed because I'm not connected to a robot and it's not turned on. You might be connected to a robot, and then if you get this lovely green light on the robot code, you can go ahead and click enable with your joystick plugged in and play around with your tank drive. So that's awesome. We've done kind of some bare minimum stuff. Let's talk about one other thing you can do for drive though. Instead of tank drive, we like to use what we've called in our code GTA drive. Rather than make it here, I'm just going to show it to you in our code. Commands, driver controls. So what I mean by GTA drive is the way of controlling a car in many racing games, including Grand Theft Auto, which is where your triggers control your speed. So your right trigger is forward speed, your left trigger is reverse speed. And if you were to do both at the same time, you would go nowhere. And then one of your analog sticks side to side is your steering. And so one way to do this is to first combine these two trigger values into one. The triggers are an interesting axis in that they only ever give you 0 to 1. So 0 to 1 on the right and 0 to 1 on the left, not -1 to +1. So what this means is if we take the right trigger, the value of the right trigger, minus the value of the left trigger, we're going to get some number between -1 and 1, right? Because we've either got, let's imagine the extreme cases where the right trigger is all the way down, so that's a 1, and the left trigger is not being touched, so that's 0, so we've got 1 minus 0. Or maybe we're not touching the right trigger, we are holding down the left all the way, that's going to be 0 minus 1, so we have a -1. And then anywhere in between is going to be a fraction. So by mixing these two signals together, we get an overall trigger value, and we could treat this like this is our speed, our acceleration, our gas pedal. Then we grab the stick, and actually in here we're just scaling this by a constant, but you don't have to. You could just take this stick and store it in a variable. And now for setting the left motor, we're taking our trigger mixture, our gas pedal, and we're adding the value of the stick. And for the right motors, we're taking our gas pedal and we're subtracting the value of the stick. So that, if we're going straight ahead and we're not touching the stick, both should be set to the same value because it's just going to be trigger val plus 0 and trigger val minus 0. If we move the stick bit to the left, we're going to get trigger value plus 0.1 on the left and trigger value minus 0.1 on the right. So maybe we're going to be at 1.1 and 0.9, and we're going to start to turn. Now that's going to get scaled down to 1 because you can't give it anything greater than 1, but it'll still do the trick, and you can do some interesting things with scaling and blah, blah, blah. So that's another way of handling your drivetrain. You feel free to copy and paste this. Feel free to look at our GitHub repository, 4627 Manning Robotics. We've got all our old code and our currently developed code on here too. So we've run a bit out of time today, so we're not going to get to the automation stuff yet. We're going to cover that in the next video. But I hope this at least got you up and running with a chassis that you can now drive around. Once again, my name's Joe Wilson for Manning Robotics, and we'll catch you next time.